All right, let's get started. My name is Kasturi Kannan, and I think some of you know me here. I think few of you were in the last course. So this is going to be a lecture on performance estimation and regularization, which is a very important topic in machine learning. Okay, so one of the key things that when you do machine learning is to estimate how your model performs when you're given the data, right? And there is a key technique on most of the times when you are doing machine learning, you'll come across what is known as overfitting, right? You all know what is overfitting. Anybody can tell me what overfitting is? Yep.
It's when you, I guess in a way, train the data to, and it learns, the algorithm learns faster some data when you try to apply it. It
Mm.
doesn't really work well because it can't adapt to other differences. Is that underfitting?
Well, yeah. So I mean, there are these. For instance, right? I mean, in general, you can think about overfitting as this, right? When you have more parameters, you can easily fit the data very well, right? So, but then it may not be the optimal model, right? So you have to strike a balance. And one of the key things is the bias variance trade-off. How many of you heard of this bias variance trade-off in machine learning? This is a very important concept. Okay, so whatever learning that you have, it's going to have two components. One is the bias and the other is the variance. And any of these models, you have to choose the trade-off between how much variance that you can give and how much bias that you can allow. So this is fundamental to any of the machine learning approaches. Okay, so there is no free lunch in machine learning. So if somebody tells you that, oh, my machine learning algorithm can do blah blah blah, one of the key things that you want to ask is that what's a bias variance trade-off. Okay, so for instance, if you have the expected value, right, so what we are ultimately trying to do is you have some data points, right, x and y, and you're trying to minimize this error, which is y is the response variable and x is the predictor variable, right? And ultimately what we are trying to do is that we are trying to minimize this error, and the expected value of this error can be written into three components, which is the variance of the response that you are trying to approximate. F hat is the function that you're, it's an approximation to the real function, and also there is going to be a bias component, and also there is going to be an error. Okay, the error, there is going to be a standard error, and that error is going to take some distribution. Okay, it could be a Gaussian or it could be a Poisson, it could be a different distribution. So ultimately the machine learning model is constrained by these three factors. Okay, so for instance, this is a figure, right, where you have the standard error. We will talk about this data set in detail when we go. And you have this three components here: the squared bias, which is the blue curve, right, and also the variance, the orange curve, and this is a test error, right? The test error is the mean standard error, right? It is made of these two components. So it goes down here, and then it takes on this curve, and it's going to go up. So this is the standard test error. This is a simulated data set. In general, you will not really know how you may not get the mean standard error, right? So there are ways we can try to find out. So that's the whole point behind a performance estimation. Okay, this is another simulated data set in which you see the variance. The variance is the orange curve here, and then the blue, and then the sum of these, the mean standard error, that's going to be given by this, right? And also you have another simulated data set. We will see these data sets, but you see that this is the MSE. The standard error is given by the sum of variance and bias. Okay, so in general, this is the testing error that you will get when you test to the new, when you have the new sample, when you have the new samples that you want to apply your model on. In general, this is how the testing error is going to be, which is going to be made of these two components. Okay, so this trade-off, right? So the bias in general, you can think of it as how much difference is there between the expected value and the correct value, right? So in general, if you have lots of data points, right, you can think of it, you can increase the parameters, you can have a different polynomial, right? You can have a linear regression model in which you can have the x, the predictor, or you can have x squared or x cubed. You can increase the components in there, right? So that's going to reduce the bias, okay, because bias is actually the difference between the expected value. So if you're like really going to every curve, every points and then drawing a curve, right, you're going to reduce the bias, because the average, the difference between the expected and the prediction is going to increase, and that depends on the different models that you use. But whereas for the variance, right, the variance is the difference for a given data point, right, how much variability is there. So you can think of it like this: if you have this low variance, high variance, and then low bias and high bias, and let's say that this is a correct model, right, it's in the bull's eye when you have low variance and low bias, and this is what we want, right? But whereas when we have the high variance and low bias, it's all going to be scattered around. So this is the low bias where you have it is on scattered around, and when you have the high bias and low variance, right, you will see that it's all going to be your clustered around this. I mean, this is just to give you an idea of what these variance and bias are, but fundamentally you have to know that everywhere you go in machine learning, you're going to hear about this bias variance trade-off, okay? So how many of you have gone through this chapters in this book, ISL? It's one of the very good books, and you will see that almost every section there they talk about, if they are going to introduce a new model, they are going to talk about the trade-offs, and there are, you know, you're going to see lots of it in this lecture. So performance estimation, so model selection and model assessment, right? There are two important aspects of machine learning. And performance estimation is a part of model assessment. So once you are building a model, you want to see how you can assess it, right? And there are resampling methods, okay? So these are the methods that are indispensable tools for performance estimation. So the idea is this: using just the data set, can we somehow assess the performance of your machine learning model, right? So the basic idea is to actually repeatedly draw different samples. So if you have a training set and we fit the model, right? So we can repeatedly draw different samples and examine to an extent in which the resulting fits differ. Okay, so that's the key idea behind performance estimation. You're thinking your testing set doesn't come from a really, you know, from somewhere from outside. It's just taken from your own data set. That's the key idea behind performance estimation. There are two popular approaches when doing performance estimation. Okay, one is cross validation. Anybody heard about cross validation? Okay, so that's one of the key techniques for performance estimation, and there is another technique called bootstrapping. Okay, these are kind of close, but they are different. We will see what they are. Okay, so the whole idea is to estimate the test error associated with a given statistical learning, right? So in general, as I was telling you, right, in general you will not know this curve at all in real life, right? Because you don't know the testing set, right? I mean, I can give you a new set. You are going to build a model, and somebody can give you another set. So in general, we will not know this at all, but we can estimate it from the given data set, right? So that's the test estimate of the test error we want to be associated given, you know, with the given statistical learning. And it's also performance estimation will also be used to select the appropriate levels of flexibility. So if you are going to have a model with x squared, x cubed, these are all different levels of flexibility that you can introduce in your model, and you can use the performance cross validation techniques to select the appropriate level of flexibility, right? And there is also a bootstrap method that we will go over on why those bootstrap methods work. For that will help you provide a measure of accuracy for your estimates, for your parameters, okay? So let's see what training and testing errors are. So you have these variables, x1, y1, x2, y2, etc., right? These are all qualitative variables. And the common approach for quantifying accuracy, right? It's the training error rate, the proportion of mistakes we make if we apply our estimate to the training observation. So we are going to test it and see how the model makes mistakes for the training set, right? But then you will realize that for the training set, the errors are going to be extremely low, right? Why is that? Yeah, it's a training set, right? So the errors are going to be extremely low. But for the test error, right, it's going to be really different, right? It's going to be associated with the test of information. For that, we are going to use the average, right? In general, we want to minimize this average. the indicator function of where the observation doesn't match the prediction, right? So that's the kind of the metric that we give for the testing error rate and the training error rate, right? For a good classifier is one where the about testing error is the smallest. So for instance, here you see that, right? You have the nearest neighbor. You all know the nearest neighboring methods, right? So that training error rate, right? It's a for 200 observation. It goes really down, right? Which is natural, right? As the flexibility 1/k increases, right? But we see that the testing error is going to be really high here, right? The black dashed line, right? And the jumpiness is due to a small size training set. If you're having a large, you will not see this kind of a jagged line. But this is the kind of errors that we are going to see, and which is what we saw, right? And why is this again like this? Why is the testing set goes in this curve? Variance and bias, right? That's what we saw the first. So we can estimate the test error rate by holding out a subset of population, right, from the fitting process and apply the statistical learning method. So it's a very simple strategy, right? It involves randomly partitioning your set into a training set and a holdout set that you can perform. I can see how that works. So for instance, here is a schematic. So what here we are doing is we are taking this the general data set, and then we are breaking it into two populations, 7, 22, 13, and then there is another. I mean, yeah, there is going to be another bunch of things, and we are going to split this into two components, and where we can test. So this is one of the standard validation techniques. So here is an auto data set, right? So in this auto data set, you can fit a linear model, or you can fit a model of degree 2, or you can fit a model of degree 3, etc., etc. So this is an auto data set. You have a horsepower that is displayed on the x-axis, right? And you have miles per gallon on it, and you have some data here, and you are trying to fit a model, and that model could be a linear model, the orange one, right? And or it could be a degree 2 model or a degree 5 model. So those are the models that is being that's been used here, right? And so you can have this mathematical form where the miles per gallon, the y-axis is given by these coefficients, right? And you have to estimate these coefficients, right? Now if we see the r square of these quadratic fit, right, we will see that the r square fit is much higher for the quadratic compared to the linear model, which means that the quadratic fit is much better fit, right? So it's natural to wonder whether higher degree polynomials will have a better fit than the lower degree polynomials, right? So we can answer this question using the validation method. Okay, so that's the key idea here, right? So what we are going to do is we are randomly splitting the observations, about 392 observation, into two sets, a training set, right, that consists of 196 of data points, and then a validation set. We are equally partitioning these two into, and then we are trying to see how the error performs, right? So here you see that at the degree 1, the 2 is suddenly the error drops, the mean squared error drops, and then it kind of plateaus here, right? So all you can say is that from here is that the second degree polynomial or a better fit, okay, if you're just plotting it just like that. But if you're using a cross validation, right, or the validation approach, you will see that there are different types of curves depending on the data sets that you use, right? Depending on what kind of a data set that you use. But all you can conclude is that the second degree is better than the first degree, but it doesn't really tell you that the higher powers are better fit, right? Because it depends on the partition. It depends on the observations that you take, and those observations determine what kind of a curve you have. You might have one kind of a split in which you find a really good partition, or in which the error could be lower. The other kind of a split, even though it is half, if you're randomly splitting, the kind of numbers that you get might really change that, right? So although it is conceptually simple, right, and easy to implement, it has potential drawbacks. One is that the testing error rate can be highly variable, right? And it precisely depends on the observations included in the training set and which observations are not included, right? So only a subset of observations are always included, right? So once when you have only a subset, you may overestimate the error rate. So that's the key problem in using this approach. Any idea on how to get it better? When you're splitting it, right? You can split it in several ways, right? So one of the key or a basic idea is to just take only one observation point out from there. Okay, that is leave one out cross validation. So all you're trying to do is just you're taking only one of the observations out, right? And then you're splitting it into two parts. The first part is just only one data set that's left out, right? You can, but then the rest of them are going to be almost the entire data set, right? If you are having n, you might have n minus 1 training observations, right? And the rest of them would be excluded, right? So that's the idea here. So here, for instance, you are having this here for the first iteration, you're taking out just one and you're trying to fit the model on the rest of them and then testing out on this, right? And then you're taking this out and then you're trying to fit it and then you're trying to okay, so this method, right? You're just leaving out one observation every time, and you're trying to fit the rest of the data, right? So this is all good, right? I mean, so if you look at the average, the mean squared average. So for the first one, it's going to be just this y1 minus y1 square, right? When you're leaving out the second one, it's going to be y2 minus the predicted y2 square, etc., etc. So if you take the average of this, it's going to be 1 by n of the mean squared error. And these are poor estimates because they are highly variable because it's based on one single observation. So each of them could be highly variable. But when you average it out, all those variability disappears, right? So in general, you will have this idea, this has less bias, right? We repeatedly fit the statistical using the model, right? Using n minus 1 observations. So it has almost the entire data set, right? So it is prone to less bias because you are using all the observations, right? In contrast to the validation set approach, in which it could be broken into half or some kind of a thing, this is better in terms of bias reduction, right? But it will not overestimate the error rate as much as the other does. So for instance, another big advantage of this leave one out cross validation is that there is no randomness involved in it, okay? Because you are performing, you'll always yield the same result, right? I mean, you're doing it for all observations, you're doing it for n observations, so there is no real randomness that's happening. It's, if you are leaving out one, that some point it's going to be covered by any other iteration. So so that there is no randomness. So this is in contrast with other validation approaches in which there is some randomness that adds to the variability, right? So here is an example of a leave one out cross validation that was used on this auto data set, and you see that the second degree is better here, right? And also here, if you do a tenfold cross validation, you'll see that there are multiple of them here. So there is a difference in these error curves compared to the leave one out cross validation, right? But then the biggest downside of this is that it will require higher computational cost, right? Because you're applying this learning method n times, right? This could be computationally expensive if n is bigger, right? Really huge. So instead, we can use a k-fold cross validation. Just we were discussing above is to randomly dividing the set of observation into k-fold groups, right? So that's the idea behind leave. That's the difference between the k-fold. In fact, the leave one out cross validation is the same as k-fold for k is equal to n. So that's only a subset of it, right? So we can get an estimate for these training data set, right? We can get these data sets for each of those, right? And we want to know whether the testing is average is small. So this is an example where we have the X. This is a simulated data set, and you have all these data points here, right? And you have a regression, which is the orange line, and you have the two smoothing spline, right? A spline is a higher degree polynomial or a piecewise polynomial functions, right? On here, you see that this is a mean squared error. As the flexibility increases, right, you have the flexibility. As flexibility increases, you see that here, right, the curve here, this is the training error and this is the testing error that goes up, and these points, right, the squares for the training and testing for the minimum that you find for these three fits here, you see those things are minimal here, right, for the first degree polynomial, third degree polynomial, etc., etc. Now this is another data set, right? This is also the same data set where uh, you have the fit here, right? You have the polynomial fit, the linear, but then here the testing data is much more. The original data is actually simulated based on a more linear scale, right? And so you see that the error here, right? The error actually drops down just based on this, right? For the second degree polynomial, the error is really closer the testing, and then you see this kind of a distribution. And also you have the simulated data set 3 here, where you have it's the data set is simulated on a much more you know, a polynomial, right? And then you see that the linear regression makes a very poor fit, right? This is to just give you an example of how the training set and the testing set may differ for a simulated data set. In real world problems, you will not have this estimate, so that's why they have simulated it and just showed how these things vary, right? So we can see how the training and testing MSE, the mean squared error on simulated data set using cross validation. For these three data sets, we can apply the cross validation, okay, and see how it performs. So this is an example where you see that the true and estimated for these three cases, right? For these three cases, in this case, the data set is simulated along a spline. For this, the data set is simulated using a straight line, using a linear regression, right? And here you have these data set simulated along this higher degree spline, and you can test these using cross validation now. Now we have an idea of how these curves are going to be based on the simulated data set. We can try to use cross validation. So we see that in the cross validation here, right? The true test MSE is blue. Okay, now since it's simulated, we know that, right? But we can also see that the tenfold cross validation is shown in this orange, right? So that's also, and also the the lay one out is shown. It's almost the same actually for the simulated data set, and the minimum, right? The cross indicates the minimum of each of these curves, and we see that the flexibility is kind of really high here, and the flexibility is really low here, right? And also here you see that the flexibility is almost 10. So despite the fact that the cross validation underestimate the true test, right, but this will come close to identifying the correct levels of flexibility, and you can really see how this is really close here, right? So the cross validation could be a very good testing method to assess the performance of your data set. And yes, what's that? Oh, how the flexibility is calculated. So you can actually see where the minimum of these curves, right? You may not really know this blue, but you know the minimum of these. Uh-huh. No, the flexibility is you start with the degree 1, you start with degree 2, you start with degree 3. I mean, so that's the flexibility. You increase the degree and you compute the cross validation metric for each of these. So, so this is the model, right? So the flexibility is the degree. Okay, your linear model is beta naught plus beta 1 x plus beta 2 x squared plus beta 3 x cube, blah blah blah. Okay, up to beta p x power p, right? So the flexibility is p, right? You have p degrees of freedom. So that's, but you can stop with p equal to 1, p equal to 2, p equal to 3. So that is the flexibility. The flexibility is the more parameters that you can use, the more degrees that you are allowing in your linear model is your flexibility. Okay, so you can find what is the best degree of flexibility using the cross validation, which really comes closer to this. You see, you really don't know the blue curve in reality, right? But you see that that's the minimum is really close here. That's the point of this. So here, right, it's very close here. So with this cross validation, you can say this, say let's say you, based on this, you find the minimum and you say that 7 is the flexibility, which means that the 7th degree polynomial is going to fit better, right? That's the idea. 7, right here in the first case, right? You have the 5, and then you have 6, 7, whatever. The minimum is around 7. What's that? Beyond? If you have a it depends on how your data set. I mean, it's see, for instance, here your data is simulated, right? Your data is simulated with almost the fifth degree here, right? Fifth degree model here, okay. But then this comes to close, but we really don't know if it is fifth degree or 7th degree in reality, right? But this flexibility, this using the cross validation, your flexibility comes really close here, right? But it need not be just 2 or 3 or 4. Your model could be anything. I mean, it depends on, I mean, your data set, how you really don't know what, but you're trying to fit it, right? Using several degrees of freedom or polynomials. You get what I'm saying? I mean, what's your question? Right.
And then normally you won't go beyond like F to 4, F to 7.
But I think.
You could do that, but the chances are you probably will over.
Yeah, well, yeah. In general, right? When you have when you also have the interpretation of what it is, right? Generally, yeah, you know, these may not, you may not really go beyond certain powers in, you know, that's right. But I mean, this is just to give you an example of what, this is just one model, right? This linear model could also be, you can apply this to a classification problem in which it need not be just a polynomial, right? It could be a different, the classification is a qualitative way of partitioning the data set, right? So you can use a k nearest classifier with a cross validation as well. So this need not be just applicable only to the powers. You know what I mean? Regression, right? It need not be only regression. It can be any machine learning scheme that you can use, right? So so the bias variance trade-off for k-fold classification, right? I mean, like I was telling you, one of the fundamental problems is the trade-off between the bias and variance. You will have the least one out cross validation will approximately be an unbiased, since there are going to be n minus 1 observations, right? And performing a k-fold cross validation will lead to an intermediate level of bias, since each training set contains these you know, n choose k observations, right? But then they are substantially more than in the validation set approach, okay? So therefore, from the perspective of bias, it is clear that the leave one out classification is generally preferred over the k-fold cross validation scheme, okay? But it will have a higher variance, obviously. When you are reducing the bias, there is going to be more variance. And in effect, the averaging the outputs of the n-fitted models, right, these will be correlated to each other. The first data set is going to be highly correlated with the second data set, etc., etc. And so the mean of these correlated quantities has a higher variance usually. Okay, and so this is going to be the biggest problem in terms of the leave one out will have a low bias, but then you'll give a trade-off between the variance, right? In general, k equals 5 and k equals 10 are typically used for cross validation to optimize the bias variance trade-off. Okay, so that's the general cutoff that people generally use. And like I was telling, right, this cross validation, you can use it with not just with regression, you can also use with classification problem, right? So instead of using the mean squared error, in this case we can see how many of them has been misclassified, right? So the cross validation metric here could be given by 1 over n, which is an average of error, where error is an indicator function of yi not equal to yi. So if this is indicator function is just 1 if yi equals yi hat, otherwise it's 0, right? You use an indicator function to use the same idea on classification, right? So everything can be defined using this metric. So for instance, this is an example from the book where they have used a logistic regression model for these classification problem, and you have this model in which the variables are given by beta naught. This is a quadratic model, right? Quadratic logistic regression, and you determine the probability, right? The logistic probability, right? This is, and then you can see these two-dimensional data set, and this is the Bayesian boundary. It's a classic boundary that separates these two, right? And then you can use the decision boundary from a linear or a quadratic model. You can stop with just this, or you can include this, or you can include a third degree polynomial too, right, on these two variables, right? And so for each of these, you are going to get an error associated with it, right? Just like this error, right? We can have a cross validation error, and we see that the testing and the training error for these, right? They are given by these two curves for this k and n classification. And if the order of the polynomial, so this is a test error. And here at least we know this is a simulated data set and you know the test error, right? But in general, you will not know it. But then here also you can see that using the cross validation, the order of polynomials are really close to what the testing error is, right? And here also you will see that as 1 over k, right? The error rate, it's minimal or close here. So this is to give you an idea that cross validation could be a very, very strong scheme when you don't have any idea of your testing set. Okay, that's one of the classic ways to do a performance estimation. All right, let's go to bootstrapping. You remember this bootstrapping? Anybody knows what bootstrapping is? Okay, so can be a very powerful technique. Okay, what the idea is behind bootstrapping is very simple, and it's highly mathematically very aesthetic. So in general, you have the variance of a random variable, right? If you have z as a random variable, the variance can be is nothing but an expectation of z squared minus e of z whole squared, right? And you have these properties of variance. And why bootstrapping works is, let's say that you have a data set here. You have the x-axis and you have the y-axis, and you have lots of these data sets, data set in which, let's say that the y is here. Okay, in the next data set, y2 is going to be like slightly above, right? And in y3 you have here, that's the data set, and this is the fourth data set. Okay, so in general, right, this is the first data set, second data set. These are completely different data sets. Okay, then you can write the expectation of yi as something like this, right? It's y times the variance of yi. Expectation of yi is just going to be y, right here, and the expectation can be written like this. And if you consider a random variable z as 1 by m over the summation of yi, okay, under the assumptions that yi's are uncorrelated, we will see that the expectation of z of this random variable, right, z 1 by m summation yi is going to be just y, and the variance of z is 1 over m variance of y. Okay, so that's the idea behind bootstrapping. So you have a random variable z, which is a summation of all yi, right? And it's going to give you these two values. The expectation is just going to be y. So your prediction is going to be as good as possible. But the variance will reduce as the number of data sets you have. If you have 1 million data sets, the variable is going to be almost zero, right? 1 over 1 million. Okay. So that's the idea. You have as much data sets as possible, right? You can reduce the variance. Okay, but we don't have several of these samples, right? We just have only one of them. So what should we do? Make a uniform sampling. Just take the first one, second or fourth one, fifth one, and form a data set. The second pass, take some random subsampling, right? And the number of subsampling that you're going to use, it's going to reduce your variance like crazy. Okay, so that's the idea, simple idea behind bootstrapping. Okay, and using this bootstrapping, you can actually have an error estimate. The error estimate, the standard error for bootstrapping is going to be square root of 1 by b minus 1 of these formulas, where these are all actually a different bootstrapped samples. Okay, so here you're taking the third sample, third sample, blah blah blah, etc., etc. In this bootstrap sample, you second, third, first, and things like that. So it could be the same, it could be different. So you're taking the sampled with replacement, you're going to have different estimates, and then this is a standard error that you can compute. So this standard error, okay, is a metric to see how your machine learning is performing, right? Because if you can bootstrap it and you can use this information, right, the standard error uh, of the bootstrapped samples to estimate how your how your machine learning model performs, because this will give you an estimate of it. Okay, so either you can use cross validation to perform and then or the bootstrapping error, but then the formula for classification for bootstrapping is not so simple as what we have for regression. Okay, so that's one of the key things we have to bear in mind. So these are the two ideas of for performance estimation. So when you don't have a new data set, either use a cross validation or you can use a bootstrapped values and then try to estimate the standard error. Okay, all right, let's go into another exciting and a very important topic in machine learning, which is regularization. Okay, so when you have the linear model, okay, so this is a linear model, you have the response variable beta naught plus etc., etc., right? If the betas j's are unconstrained, they can really explode. Okay, so they can be really exploding, and so they are susceptible to high variance. Okay, when you don't have any constraints, these variables can be really huge, right? So to control the variance, we may want to regularize the coefficients. Okay, so we may want to shrink the coefficients. That's the idea behind regularization, or they are called shrinkage methods. Okay, and there are two best techniques for it. One is the ridge regression, the other is a lasso regression. So these are very standard and very important regression techniques. Okay, so it's very similar to least squares. Everybody knows least squares, right? And then it's similar to least squares. In the least squares, you have the RSS, right? The residual error is given by yi minus the beta j of this, right? In ridge regression, what you do is you add a parameter here, lambda, and also you have the summation beta j square, right? So what you're trying to do is you are trying to reduce this quantity. So I mean, this is a tuning parameter, right? And this additive term is called the shrinkage penalty. So like if lambda equal to 0, it's same as the least squares, right? You are adding just this additive term, right? So unlike the least squares that produces only one set of coefficients, the ridge regression, depending on lambda, right, it's going to produce several set of these coefficients, betas. Okay. Now the penalty, you may think that why this penalty if you think it's starting from 1 to p, not 0 to p, because the beta term represents the mean, right? When all the other the features are 0, the initial is going to be the mean of that, right? So that's why the penalty does not apply to the beta naught, right? So the one of the key question is how do you really choose this parameter lambda, right? So we need to have a disciplined way of selecting this parameter lambda. So that's called tuning, right? So in the original paper, right, these guys introduced how to find these parameters. So they plotted these coefficients, and then they chose this coefficients such that they were not rapidly changing, right? Or they had some sensible signs. But then it didn't have any objective basis, and this was heavily criticized. And now the standard practice is to use cross validation to find this tuning parameter. Okay, so we will see that in the end of this lecture, but the key idea is now to use cross validation to select this tuning parameter lambda. Okay, this is in the standardized ridge regression, right? You have these coefficients, you have this data set where you have income limit and rating and student, and you have the parameter lambda, the tuning parameter lambda, and the standardized coefficients here, right? And you see that these ones, right, they are like this, right? They have you see that as lambda, right, as lambda increases, right, the shrinkage actually happens, and you have these coefficients are going to 0, right? And when lambda equal to 0, it's going to be a least squares, which has a high variance, right? So that's the idea. And also you see this is beta lambda of r by beta. This gives you an idea of how the coefficients. So if lambda equal to 0, right, so that corresponds to beta naught. So this is going to be 1, right? So this is going to give you an idea of how these coefficients vary as they increase, right? So when it's going to be 1, right, the standard coefficients for this income is going this is the income. So this is to give you an idea of how the tuning parameters could be selected and how the standardized coefficients could vary depending on the on the tuning parameter. But this is not scale invariant in the sense that if you scale it up in the linear regression model, right, if you add a constant here, it's not going to change anything, the coefficients. But when you have these ridge regression, it's going to change in general. That's why we need to standardize the predictors to the same scale before you can apply ridge regression or lasso of any of these models. Okay. So what's the advantage? Does ridge regression improve over the least square? So here you see that you have the lambda parameter, right, for that, and also the mean squared error for this data set. Now you see this is the variance, the green is the variance and black is the bias, right? And also here you see this coefficients beta lambda of r by beta, that gives you an idea of how these uh, how the coefficients vary, right? So we see that the regression and this is the smallest where that happens, right? So for lambda parameter you can actually choose um, actually you can choose the lambda parameter such that through cross validation, we'll come more that later, where this is minimum. But the general idea is it will have a decreased variance, but obviously you will have an increase in the bias as lambda goes to infinity, right? So when it comes to relationship between the response and the predictor variables, right, when it's close to linear, right, the least square estimate will have a low bias, but it will have a high variance, and a very small change in the data set will lead to a very big change in the coefficients. Okay, and when it is going to be n, the least squares will be highly variable, right, and the least squares will not even have a unique solution there actually, because when you have higher number of data points, okay, or the number of predictor variables is bigger than the number of data points, right? The equation is severely under constraint, right? And so the least squares will not even have a unique solution, whereas ridge regression can really perform well. Okay, so in general, ridge regression can work best when you have to reduce the variance, right? But the biggest problem with ridge regression is that it will include all p predictors, right? It has all p predictors, right? And none of them will be 0. right? So which means that you have to include all the predictor variables in your model. So the interpretation might suffer, right? But I mean, you can say, you can ignore that. Okay, if the coefficients are going to be really, really small for some of those variables, you can ignore that, but still it will not be zero, right? So we need a method in which it can be absolutely zero, and that is given by this model called a lasso. Okay, so this also performs variable selection, right? But identifying a good tuning parameter is essential for performing that. So lasso is just similar to ridge regression, right? But the only thing is here you have the squared norm, but for lasso you have the L1 norm. Okay, so that's the idea behind lasso. It's just one of the but it's a very strong model actually. It gives a null model where all the coefficients are zero when lambda becomes large. So when lambda becomes large, all of these are going to be just zero. Okay, so here, for instance, in this you see that as lambda increases, the first is the income, and the second comes what's this? This is the student, right? The student. I think the orange one is the student. The first is a rate. Actually, the first is a rating here, right? That appears here, right, in this coefficients, and then you have the second is the limit, and the third is the rating, and then the student. So it appears, each of these appears one by one. Okay, so that's the biggest advantage, that you can really see. It not only gives you the best coefficients, but it can also give you a feature selection right there. Okay, so that's one of the strong points of doing a lasso over ridge regression. And actually there is another formulation of lasso and ridge. It's just, instead of having that L1 or L2 norm, you are just constraining all these beta, right, to be lesser than S. So for every value of lambda, there is some S such that the lasso and also these two equations will give a good estimate, the same estimate, and also for this for ridge. So ridge and these are alternate formulations for lasso and ridge. Okay. Oh, so that's the idea behind lasso and ridge, and why actually, if you think of why lasso gives you that zero, right, for those variables, you can see that when you have this constraint, right, you have this constraint of beta 1 squared plus beta 2 squared is less than or equal to S, right? This is the ridge regression, and this is the lasso, right? And you can see that at least in 2 dimensions, this is going to form this square, okay, rhombus, okay. And whereas for ridge, it's going to be the circle, right? And let's say that these are the residual, the coefficients, and all these are all the residual RSS, right? Squared error and contour lines. So all of these RSS are going to have one value here, and this is RSS is going to have another value here. RSS is going, but then you see that this could meet in the corners, whereas for here it may not meet. There is no corner here, right? So it may not, so that's why it's not zero. Here that just meets the zeros. The zero happens exactly where this square meets this rhombus, right? So general, right? In general, the ridge regression estimates may not be zero, whereas for lasso, right, the ellipse will often intersect in the constant region. So when that happens, the coefficients are going to be zero. So that's why there is a reasoning behind these, why this happens. And when you see the ridge versus lasso, here you see that the squared base. So here you have lambda parameter, okay, and you can see using all 45 predictor variables, right, you don't really see much difference between ridge and lasso. So this is the lasso, and this is the ridge, right? If you look at these two later, whenever you have time, it's almost going to be the same, right? I mean, it's not really different. Yeah. What's it? Lasso. I mean, all these methods are designed to actually. Uh huh. No. Overfitting. See, overfitting is doesn't actually. These are designed to avoid overfitting, right? Because so this is just a residual error. This doesn't tell you anything about overfitting. You can't anyway deduce any overfitting through this. The overfitting happens when your coefficients are going to explode. That's why you are designing this method so that you want to restrict and shrink some of those coefficients so that it doesn't explode, right? So over these are methods just to avoid overfitting. Okay, so that's the main idea behind lasso and ridge regression is. But then this doesn't give you any idea of what overfitting is. All it says is that when it meets this, right, in these boundaries, it's going to be this is going to be zero. The coefficients are going to be zero here, right? This is the RSS, the residual square, right? These are the RSS, and all these the points will have the same residual error, right? And when it meets here, right, at least here you don't, it doesn't have to meet here, and so it's not going to be zero. But when you have this constraint with lasso, it's going to be zero because exactly it meets the cut, right? The error is going to be zero, so that the error when it meets that, it's going to be zero. You see that? So that's the, but you can't really do any overfitting under that. In fact, lassos, in fact, better than ridge regression for overfitting. So here, for using all 45 predictors, right, you really don't see, this is lasso. And this is an example, this is where you see that there is a ridge and the lasso is given by this error, right? The ridge is given by dashed, the lasso is given by the solid, and you see that the variance is almost the same. I mean, the bias is like almost the same. The variance is also almost the same, and so you have the bias plus variance, which is error going to be almost here, right? But when you just use two of the 45 predictors, right, instead of using all 45 predictors, which ridge gives, whereas lasso is going to put some of the predictors to be zero, right? You will see that here the variance is almost the same, but the bias, right, really gets reduced. Okay, so the bias is going to get reduced, and so the lasso performs much better than the ridge regression. Okay, but yeah, the question of overfitting, which is among these two, you can ask which is which may likely overfit the data and which may not overfit the data, right? So in general, right, neither ridge nor lasso will universally dominate each other. So it depends on the number of predictors variables that are used, right? So one may expect lasso to perform better in a setting where relatively small number of predictors are there that have substantial coefficients, right? The remaining of them are zero. And but then the ridge regression will perform when you have many predictors, right? And if you already know the number of predictors, if they are related to the, I mean, if you already know that all of these predictors are kind of are almost equal, then ridge may perform better in that case, right? But then in the general, we do not know what's the number of predictors that are going to be there in the data set, right? So, but then one of the biggest advantage of ridge over lasso is that it performs variable selection, right? Now, the question of how do you use the tuning parameter? So it all depends on what the tuning parameter is. One of the simple ways is to use the cross validation, right? You use a grid of lambdas, right? And you use the cross validation for each of these lambdas, and then you fit the model to see where the minimal error happens. So here, for instance, here, this is the minimal place for lambda. The error is the minimal, right? For each of these, can do for each lambda you can do a cross validation, and then figure out which one is the smallest one, right? So for that you can actually choose that. So here are two examples. You have the vertical cross validation here, and so this is where the smallest cross validation happens. And you look at lasso here, at the place of where the smallest cross validation happens, you have the selection that's going to be optimal. Okay, so that's the two predictor variables the lasso gives you, right? According to where the tuning parameter, you're just going to have the coefficient that correctly gives the uh, coefficients for these two predictors. Okay, so this also, right, I mean, this corresponds to a set where the rest of them are zero, right? It just gives you that exact place where you have the coefficients corresponding to the lasso. Okay, so cross validation along with lasso, right, it correctly identified these two signal variables in the model. Whereas least squares assigns a large coefficient. Least squares is where lambda equal to 0. The lambda equal to 0 corresponds to this one, right? It assigns a large coefficient here. So at the end of the day, when you have ridge or lasso, when you're doing to do feature selection, you always use lasso. That's better, right? And also when it comes to tuning parameters, you do by cross validation. And some of these things actually are implemented in many of those algorithms out there. Uh, do you know Veka? Have you used Veka? If you don't, it's one of the nice machine learning algorithms. It's point and click. It's very easy. So, but then you're also learning what other TensorFlow or something. No, what other package are you using for machine learning? You're not using anything. Okay. I mean, see, most of these things, right? It's also hacking. You have to download some of these things, and then also, like there are so many options now to learn, right? There are so many tutorials out there. There are Udemy, there are edX, and there are Coursera. They have all classic machine learning things. I mean, some of these things you can get it by yourself, right? I mean, it's good to know the theory, but you have to practice some of these things. There are so many data sets out there. Just try, and try to get some of these things worked out. I think that's the best way to learn, actually. All right, so I think we'll stop with this, and Sophia has some demo for as a part of the lab. Right.